Now, a lot of times the type of igneous rock that you get is completely dependent on magma. And basically we classify magma in a lot of different things. But the main way that we classify magma is based on the silica content. Yes, Brandon? That's calcite. We'll talk about how that forms later on. Right now I'm just trying to get you guys curious enough. Eventually we'll answer why the sky is blue, Austin.
We already answered that.
Did we? Okay,
Yeah.
good.
That is orange, though.
I'll be quiet
It can make sense.
It's because of the color of the ocean.
It's not because of the color of the ocean. Don't make it mess.
Alright, so we classify magma based on the amount of silica that it has. Silica is like glass. And if you heat up sand, you get this clear liquid and it forms glass. But it's very gooey. Have you ever watched anybody handle a glass before? It's a very, very gooey substance, right? Okay. So what happens is if the magma has a high levels of silica, is that going to move easily or slowly? Why?
I heard what I was trying to.
So if silica is really gooey, is that going to allow the magma to move more easily or more slowly?
So it keeps getting harder.
Yeah. All right, and that concept of resisting the flow is something that we call viscosity. Okay, so viscosity is basically, well, if something is viscous, it means that it resists flow, right? It doesn't really move very fast. An example of viscous is molasses. All right, that's like a very, very thick type of syrup, almost like a sugar. And even in July, molasses moves very slowly, let alone in January. Okay? So, molasses is very viscous. Now, the measure of how viscous something is called viscosity. So, it's the measure of viscous. Yes?
How come like in this one you have the like shiny crystals and then you have like the darker?
The calcite thing?
Yeah.
We'll talk about that. So, again, the higher the silica content, the more viscous the magma becomes. Now, let me put this, put to you this way. I want you to compare and contrast two types of volcanoes. Mauna Loa, which is where? Hawaii. And St. Helens.
Westland?
Washington State, right? Okay.
Mauna is more active.
Yep. Now, hold on. Compare and contrast their types of eruptions. Whose is more violent?
St. Helens.
Why is St. Helens more violent than Hawaii?
Because it keeps itself controlled for so many years, and then when it erupts, it goes all out. But when in Mauna Loa, it erupts daily, so it's not going to have so much pressure to blow out of it.
Not a bad analysis. It's close though. No, we actually did expect that one to go. The difference is in the type of magma, which is why Mauna Loa is able to erupt every single day to remove the pressure, and why St. Helens is not. Okay. It's all about the type of magma. The type of magma underneath Mauna Loa has a very low silica content. So what does that mean? It's allowed to run really easy, right? Just as it comes out and oozes all over the place. So it's able to flow very easily. It's very low viscosity. The magma underneath St. Helens has high silica content. So therefore it's able to come out of the vents very easily. If I have a high silica content, am I able to flow easily? As we respond to that question. Okay, so high silica means I can't flow very easily, and if I can, does that increase or decrease my chances of getting plugged? increases. So what happens is because of the high silica content, I've created a plug within the volcano. Now the pressure starts to build, and then eventually you overcome the pressure, and then that's when big bad things happen. Okay, so that's all based on the silica content. Now we have some other things about magma to consider, and that's these four concepts right here. The temperature of the magma determines the type of rock, the pressure at which the magma is being kept, the amount of water. Now this is interesting. Water versus melting temperature. Does water increase or decrease?
Decrease. No, increases.
Does water increase or decrease the temperature at which something melts? It decreases it. The more water content that the magma has, the easier it is to actually melt the minerals within the magma. So it actually decreases the melting point, which is really almost contrary to what you would normally think. And that's because of that water gets heated, it creates steam, and then that extra energy allows the minerals to melt faster. And then we have the mineral composition. So what types of minerals are actually within that magma? All of those contribute then to different igneous rocks. And in fact, if you want to know what type of magma is sitting underneath the volcano, all you have to do is do what? You gotta look at the rocks. See, the rocks tell us everything you need to know. They'll tell you where your relative area has been. It tells you what it's going through right now. It's going to tell you where it's going in the future. The rocks, all you have to do is be able to read the story of the rocks. It's not any different than when archaeologists were trying to learn how to read the hieroglyphics of Egypt. Once they figured that out, they were able to then build wonderful past histories of a long-forgotten civilization or culture. And this is what geologists do today. We look at the rocks, and now we understand how these different rocks form. We are then able to build an understanding of what it was in the past. Alright, so I'm going to stop.